So hi everyone, I'm Sagar and I am a PhD student in Astronomical Observatory, Jagiellonian University. And so welcome to our summer session of the Nuts Talk. And so this time we will read more about or learn more about the radio universe, which is a follow-up talk of my previous radio universe talk. And so let's start our presentation. Yeah. So, so we are we are foreign PhD students in astronomical observatory of Jagiellonian University, and we are conducting a science popularization program. The name of our program is Night and the Stars, and here is the team. We usually organizing monthly outreach programs in our observatory, which is live one, and but due to this pandemic we are not able to do this anymore, and we are doing our online talks, and here is our beautiful observatory photos, and hope so the situation is going better in Poland, and we will start our offline observatory regular outreach programs. So let's start our talk. So I will first go with basics of electromagnetic spectrum, then about a, also a small brief introduction, brief part of my from my previous talk. Then we will move toward our main topic. So yes, so here is the first, so that we maybe all know about those things, and but it's still required to revise those small things that we will going to use further, so that it will clear for scientific things also. So uh, so this is a what we know this wavelength and a frequency. Wavelength is like the distance between the two crest of a wave, and frequency is like how much wave is passing through a particular in a particular time. So so now uh, the thing is how we can see an object. So we can see any object when a light is reflecting from the source and it is coming to our eye. So our eyes act like a detector, and it can recognize the light and we can see the object. So the electromagnetic spectrum, like, is not only what our eye only see. There is a whole range of shorter to longer wavelengths are there present, and together they are called as electromagnetic spectrum. And the longer the wavelength and the shorter the frequency, and vice versa. And here you can see the frequency is increasing and the wavelength is decreasing. And when the frequency is less, the wavelength is more. So here is the electromagnetic spectrum, which is ranging from gamma ray to radio. And here you can see that uh, which type of electromagnetic spectrum penetrate to our Earth's atmosphere. And you can see that the ultraviolet, X-ray, gamma ray, even a microwave doesn't penetrate our Earth. So, and you see that this is the size of the electromagnetic spectrum, like for all type of waves. So radio waves are larger, like 10 to the power 3 meter, like kilometers, and here is the microwave wavelength, which is size of a human, and then accordingly you can see the size of the different type of electromagnetic spectrum. So each wavelength is corresponding to a frequency, and also each wavelength is corresponding to a temperature. Like different wavelength have different temperature. So now the radio wavelength, because we are going to focus on only radio waves and radio objects. So that's why we need to know this. So the radio wavelength is ranging from 1 millimeter to 10,000 kilometer. You can see that 10,000 kilometer is longer than the radius of the Earth. So one microwave is 1 centimeter to 30 centimeter, and millimeter waves is because the again the radio wave is subdivided into four parts: microwave, millimeter waves, sub-millimeter waves, and radio waves. So I will basically focus on radio waves. I will ignore microwave, millimeter, and sub-millimeter waves. So longer the wavelength size of the telescope, and you can see the um, you can see the very finest structure from the from the universe. And also the traditional optical telescopes are reflector and refractor and compound types, whereas the radio telescopes are like antenna types, that the dish antenna that you have seen in for television broadcasting transport. So because the radio waves are longer, and so that's why we need a bigger telescopes. So now coming to the atmospheric window, that how much electromagnetic spectrum entering to our atmosphere. So you can see is the opacity versus the wavelength map. The X-ray, gamma ray, and ultraviolet lights are blocked in our upper atmosphere, and visible some part of infrared are only coming to the ground level. So you can see that this is the ground of our Earth, and this is our atmosphere. 0% is our ground. So how much, what type of electromagnetic spectrum is penetrating to our atmosphere? So in the end, you can see there is a long radio wave which is blocked by our atmosphere, but still we have a very large part of our of radio waves which can penetrate our atmosphere, and we can catch them in our ground-based observatories from the source. So, due to the atmospheric opacity of our for the electromagnetic spectrum, we require sometimes we require ground-based observatories, and sometimes we require some observatories like which is rotating around the Earth in the space. So here you can see from gamma ray to radio, there are several type of observatories are mentioned here. Those are some famous observatories, and you can see in the radio regime there is Green Bank and VLA telescope is there, and they are all are ground based. So because of the optical wavelength can penetrate to our atmosphere, so we have a small part of this electromagnetic spectrum, and here we have some ground based observatories also. So I want to mention one thing here, that each telescope always require a development of a new technology, which also has an n number of application to our mankind. So now coming to the one of the important thing, the astronomical scale length. Um, one in astronomy, the objects are very far from us, and it is require a very convenient scale where we can measure our distance in a convenient way. Like so, let's say the light speed is for 1 second is 3 lakh kilometer per second, and you can see the one light minute. That means how much light can pass in a entire 1 minute. It is something 18 into 10 to the power 6 kilometer per second. So to imagine this 1 second of light speed, you can take the circumference of the Earth, which is 40,000 kilometer, and you can see that the light can rotate around the Earth 7.5 times per second. So light is really fast, and there is a way. So there is a reason why we are using, why we astronomers are always using light speed as a distance measurement. So yes, so you can see this very beautiful video made by this YouTube channel. You can see the this is 60 light second. That light is coming from sun to Mercury, Venus and Earth. So you can see in only 1 minute it can come halfway to the Mercury, and which is only 1 light minute, and Earth is already 8.3 light minutes away. That means when light is started from sun and it is reaching to the earth, it is taking around 8.3 light minutes. So light, although it is the light is associated here, but light minute is a measurement of distance. So later we can see there are Jupiter, Saturn, and Uranus and Neptune, and there are the farthest planet Neptune is 249 light minutes away because Pluto is no longer a planet now. And coming out from the solar system, we have our nearest star, which is Alpha Centauri, and you can see the distance between Sun and Alpha Centauri is 2.5 million light minutes. So when you will convert this light minute to kilometers, it will give you a huge number. And again, we even if we choose the light minutes, it is again giving a 2.5 million light minutes, which is again huge number. So to make it simple, what astronomers did is they took the light year, that how much light can pass in 1 year, which is a light year. So the 2.5 million light year is 4.4 light year here. So you can see that how light is reaching to the Alpha Centauri, and so here different stars from the Big Dipper, and you can see there are 69, 93, and one is 360 light year away from Earth. And so that's why light year is one of the convenient way to choose in distance. So there is another distance that often we are using in very large scales in cosmos, which is 1 parsec. So it is slightly, you can say that like we are using different type of scales to measure the distance, but saying a big number then a convenient way to say a small number is always like always helpful, that you can remember easily and you can interpret easily also. So here 1 parsec is when 1 arc second is subtended by one astronomical unit, then the distance between two sources is 1 parsec. So 1 parsec is 3.6 light year. And yeah, so now let's move to our radio universe recap that I have said last um, in my last talk. So here is the sun, a Jupiter, and a galaxy, and an elliptical galaxy, Hercules A. So it is look like something different in radio wavelength when it's like a same universe which is sharing to us with a like a parallel universe. You are just looking a different type of things actually. So Jupiter, radio Jupiter have like two side of lobe like structure, and sun is completely looking different. There is no flares, and the galaxy. For the galaxy, the jet is coming out of nowhere, right? In the radio regime. So yeah, we will see it later about the galaxy, but this is the fascinating thing about radio. And now coming to another galaxy, which is Centaurus A. We will see it later for also, but let's how it look like in optical. In optical, a dusty lane is there around in front of the galaxy. In infrared, you can see something different picture. In UV, you again see little bit similar to optical, but some different parts are also visible. And in X-ray, it's a completely different thing again. The small jet is coming from this, and again the hot gas is present around the galaxy. And for radio, the same. the bipolar jet is coming from the center, and it is creating lobes there. So each wavelength is telling to different story, which corresponding to a different processes, astrophysical processes happening in the galaxy. So now let's talking about a thing about the hierarchy of our universe. So we know we are staying in our Earth. So first we can see that we are in the planetary system. The planetary system, then we can which is we known as the our solar system. So after that we can see there are stars, and even if when you again come out from, like even if you zoom out from the stars, you can see there are cluster of stars. Then cluster of stars, again they made a galaxy, and galaxies are again they are grouped together and they form galaxy cluster. Then local cluster is forming, and then the filaments and the superclusters. The hierarchy of our universe is too high. We can see one in planet scale, like we humans are only maybe maximum we have 7 feet, like and you can see the superclusters are like one supercluster in a range of in megaparsec scales. So like the difference in distance is so high. We if we see the 1 parsec in meter or kilometer, then it will take a huge, like huge number. So it's good to mention in parsecs. So now coming to the radio galaxies, you see this is a spiral galaxy, which is like our Milky Way galaxy, and this the diameter of this galaxy is like normally diameter of a spiral galaxy is 10 to 60 kiloparsec, and here is a active galactic nuclei, like when a galaxy center is very active and accreted with more matter with supermassive black hole, then it emits a bipolar jet kind of thing like this, and it is span over the entire space. And you can see that the same galaxy is emitting the radio jet. The image is not scaled, but you can see that if you take this spiral galaxy and fit into this radio galaxy, it will fit into the tiny core. And sometimes we call those type of galaxy which are very active, those are active galactic nuclei. And the size of the source is in range of sometimes hundreds of kiloparsec, and here you can see is like just 60 parsec for a spiral galaxy. This is another famous galaxy which is Centaurus A, and you can see like that we have discussed before, the different X-ray, radio, and optical parts which is visible properly here. The galaxy's central supermassive black hole accreting the matter, and it is emitting the bipolar jet in both direction, and those are radio lobes, which is after hitting to the medium they are accumulating there, and they are creating lobe. It's something like when you are taking a jet of pipe and it hit to the water and it is just stopped there. It's something like this, like either the wall appeared or the water is just getting slower, or it just lost its angular momentum. So this is another galaxy that I have taken from Chandra website, and also it's a picture A, and which is in my poster also. So the same thing is there. A tiny galaxy is here with supermassive black hole, jets and lobes are coming out, and this is basic structure of a radio galaxy. A core, a jet with a lobe. When it is hitting to the medium, a hotspot is created, and yes. So, so this is a galaxy comparison chart. You can see that same Hercules A galaxy which is a famous chart. You can see that how tiny our optical galaxies look like compared to their radio counterpart. So this is the uh, like uh, that's why radio like each electromagnetic spectrum is very special, and for me radio is very special because we can see jets, and we can see the how the black hole is really emitting the large amount of emission out from the galaxy, because because it require a high amount of energy and high amount of momentum to take out the particle from central supermassive black holes to the um, almost hundred of kiloparsec away. And there is another type of radio galaxy is there, which is white angle tail radio galaxy. Here we can see that the both jets create a um, angle, and which is like maybe you can say it's a narrowing it's an acute angle, or maybe it's a then it is a narrow angle tail one side, and another side it's a wide angle tail. And then this is also another example of narrow angle tail, um, like this, or a head tail, like the galaxy is bent in such a way that the lobes are look like a tail, and there is a the core, and near to the jet it look like a head, and it is moving toward something. And there is another type of galaxies are there, which is except radio galaxies. They are very interesting type of radio galaxies. Sometimes they have binary black holes, and they are spinning, so that along with the black hole the jet is also spinning, and they are creating except radio galaxies. And yeah, there is another type of radio galaxy is there, which is called double lobe radio galaxies. Something like when there is two restricted activity is present for a radio galaxy, like you just take a pipe and uh, switch off your pipe for some time, and then again switch on your pipe, then you will see the two activity, a like two activity of water in pipe, something like here also the jet is switching on one time, and again switched off for some time, and again it is restarting, and that's why it is creating double lobes. Like this is the first emission, and here is a lobe, and this is the second emission, and here is the lobe. And there is some peculiar kind of radio galaxies are also there, which has spiral host, and generally we have elliptical galaxies at the center of radio galaxies, except 12 or 14 radio galaxies found whose spiral galaxies um, uh, are the host. So this is a megaparsec jet is coming, and I will come to this like how the megaparsec jet is there. And there is another galaxy which is a triple double lobe radio galaxy. Like here the jet activity is three time is happened here, and like three times switch on and off the radio jet from the center supermassive black hole. And the the extreme type of radio galaxies are known as the giant radio galaxies, whose size is greater than 700 kiloparsec, and yeah, and those are till now discovered only 1,000 giant radio galaxies. And yeah, so how a large giant radio galaxy look like? So you can see the 1 megaparsec is equal to 33 times Milky Way galaxy, and here is a comparison for the Milky Way, that how tiny it is. And yeah, there is another scale comparison that I took from Pratik Davade paper, um, uh, and you can see this is the largest giant radio galaxy discovered till now, which is almost 5 megaparsec in scale. This is discovered by one of our professor here in our observatory, Professor Mahalski, and you can see the different type of radio galaxies and their size. This is the tiny radio galaxy which is known as Cygnus A. So in previous slide we have seen the Hercules A, how big it was from the spiral galaxies. Now you can see the largest giant radio galaxy, which is around 5 megaparsec, and here it is 0.5, almost 0.5 megaparsec for Hercules A. It's almost 20, almost, yeah, 20, sorry, almost 10 times size of the um, Hercules A. And yeah, so for this talk I skip all my technical stuffs, like how radio galaxies are imaging and how radio imaging are done. So I will talk in the next part of my radio universe part 3. And yeah, you can just post your questions, I will see and I will comment and I will answer those. And yeah, thank you so much for joining us. And I will wait for your questions and I will come back within just a few seconds. How to mute? But wait, you have to take question, no? Question will come. Yeah, just mute. Ah, okay. Dismiss. So there is a question by Syed Umer, that the outgoing emitted particle energy is greatest at the jet region or the lobe. What determines the length of the jet? Yeah, so this is the main one of the main fundamental questions of radio astronomy. Sorry, in the field of radio galaxies, what determines the length of the jet? So first, the particle energy is greatest in the jets. Um, like there is two type of things are there. Like just a second. Okay, so I'm coming to this one. So this is the core, and you can say this is the jet, and this is a lobe. Uh, so particularly starting from here and moving toward the lobes, and the speed is always greater in jets when it started, and then while reaching to outward to the lobes, it is slowing down. But as in terms of energy, this is emitted before this part, like this is first created and then it was created for the radio galaxy, as you were seeing the some past of this radio galaxy. So the in current um, situation, in the present situation what we are looking, the jet particles have less energetic than the lobe particles. In lobe we have depending on the where you are looking for, toward the hotspot they have more energetic particles, and away that we have less energetic particles. And what determines the length of the jet? So it's simple, like you can say that it the speed of the jet, the density around the galaxy, and also the how can I say, also the uh, magnetic field, sometimes it is also responsible for the length of the jet. And it's something like that, when you have a uh, water pipe and you are throwing the water from the pipe towards a wall or towards something, when a wall appeared then it will stop, otherwise if you slow down the water speed then also it will stop in between, so something like this. So it is interplay between the jet speed or the environment density. Yeah. And there is also, does less radioactivity means there would be less star production in that galaxy? Certainly no. Also, so apart from feedback process, Asian feedback process, the optical galaxy is very tiny compared to the radio lobes. So that uh, that may not be a less stars production in that galaxy. Yeah. So this is related to some very detailed intriguing scenario, how the accretion rate is going on, and how matter is falling toward the accretion disk, and how much radiation is coming out, whether the galaxy is a high accretor or it's a low accretor. Yeah, there are so many things, so many factors are responsible for radio activity, like how it is switched on and how when it is switching off. So um, yeah, maybe I will comment you said that how you will see in details, like there are several papers from different radio astronomers, or from from different high energy astrophysicists, that how jet is emitting. Yeah, and there is, I think, another comment or question. Okay, so now there is no other questions. Maybe I will wait for some time. So someone commented like, glad to know that galaxies doesn't look like those pictures of galaxy we usually see. I think yes, but yeah, in different wavelengths. Yeah, yeah. So thank you everyone, and thank you for commenting. Um, thank you Anita, Anastasia, Sutos, Sandeep, Syed, and other peoples that who have commented in my previous video that you deleted. Maybe Subrata, Arpita, and yeah, and thank you all. Like if you have any question, any doubt, just please post here. And yeah, and yeah, we deleted our two previous video because of some problem. My friend Uni Krishnan Suresh Kumar, he just saved me, and he set up my microphone and speaker. So yeah, you can visit his two talks that he have given. So 2 or 3 talks he have given in previously, and which is very good, and which is very that you can know more about our universe and different from different PhD students. And yeah, just stay tuned for our next talk. We will still figuring out who we're going to present next. And yeah, stay tuned, and hope we uh, do our population work as a front to front, or maybe not online, and which will be very good. Yeah, and thank you. Good night, take care, bye everyone.